So, good evening, everybody. Welcome back to our seminar. The speaker of today is Professor Alessandro Gnoatto. So, he's an associate professor of financial mathematics at the University of Verona. And before joining Verona, he has been a quant at Bayern LB at the Counterparty Credit Risk Front Office, and before a postdoc in the work group of financial mathematics at the LMU in Munich. His research interests include multiple curve interest rate and cross-currency models, counterparty credit risk and funding, computational finance, machine learning methods for PD, and affine processes. So thank you very much for accepting our invitation. Alessandro, the stage is yours.
So thank you very much, Sarah, for the introduction. And first of all, I would like to thank the organizers of this seminar series for giving me the opportunity to present my work. So this talk is divided in two parts, and this is reflected also in the title of the talk. So we will talk about Deep xVA in the first part, and in the second part we will be talking about a solver for a backward stochastic differential equation in the presence of jumps. So the first part is based on a work with Atena Picarelli, who is here in Verona, and Christoph Reisinger from Oxford, whereas the second part, the second work in progress on the solver, is based on a joint work with Marco Patacca and Atena Picarelli, who are both here in Verona. So, of course, this is the seminar series on machine learning in finance, so I don't need to tell you that machine learning and in particular neural networks have become very popular recently in finance. Historically speaking, neural networks have been quite popular on the so-called buy side, so I put the physical measure near the buy side, and they have been used there in order to forecast time series, detect trade signals, or find optimal trading strategies. Quite recently, we have seen a surge of interest from the point of view of the sell side, so I put the risk neutral measure here. And in this area, we see approaches to represent parametrized models in view of model calibration, or approaches in order to learn the value function for a certain contingent claim in terms of variables such as the spot price or the strike, and to learn hedge ratios. So what we are going to discuss tonight is close to this idea of learning hedge ratios, although this will be clear in the sequel. So, of course, you all know the nice picture of neural networks, so I decided not to put it in the slides. For us, a neural network is just a function from RD to RD, at least for this presentation, which is a composition of functions, some of which are affine transformations, which involve a matrix of weights and a vector of biases. You compute this affine transformation, and then you apply to each component of the vector a so-called activation function, and then you send the output to the next so-called layer. By gluing together several layers of this form, you obtain the classical feed-forward artificial neural network. And sometimes during the talk, I will be just regrouping all the parameters of all matrices and of all biases inside a single vector row. Okay, so what is the first part of the talk about? So the idea is to use deep learning methods in order to compute certain quantities which are known in the literature as valuation adjustments. Valuation adjustments have emerged in the aftermath of the financial crisis with the idea of including in the valuation of derivatives of contingent claims several aspects such as the possibility of default of all the counterparties involved in the transaction and several funding issues. So the computation of these valuation adjustments is quite involved, and essentially they require you to know the whole evolution of a certain contingent claim. So you don't just need the conditional expectation at time 0, you really need to know how your contingent claim is evolving over time and over omega. Okay, so we need essentially to generate scenarios for the future values of a portfolio of contingent claims. Okay, so the idea that we want to propose is to generate such scenarios for the price of contingent claims by means of the so-called Deep BSDE solvers. And once we generate the scenarios by means of the Deep BSDE solver, some of these valuation adjustment can be computed by simply performing an integration with respect to the time dimension and then taking sample averages. So this is just for the basic valuation adjustments. There are, however, some more involved valuation adjustments that feature a recursive structure, and for these more involved valuation adjustments, what we propose is a nested application of a deep learning, of this deep learning method in order to approximate backward stochastic differential equations. So, just to set up the scene, okay, we consider a set of risky assets, okay, S1 up to SD, and they follow the canonical process for the first part of this talk. And we are interested in European claims for simplicity, and we have a portfolio of contingent claims. So capital M is how many contingent claims are traded between a bank and a certain counterparty. Okay, so we can simply think about the value of each of these contingent claims as V hat small m having this classical form, okay, for n ranging from 1 up to capital M. So it is well known that each of these V hat can be computed by solving a forward-backward stochastic differential equation. So this is essentially the theory which is very well explained in the classical paper from 1997 by Karui Peng-Knetz. Okay, so you have the forward dynamics of your risky assets, and then you have this backward dynamics. Okay, this is the dynamics of your contingent claim, and the objective when you solve the BSDE is the following. So given the terminal condition of the BSDE, which is given by the payoff of your contingent claim, you are looking for an optimal hedge strategy, okay, and for the value function V. Okay, so solving the BSDE gives you not only the initial value of the conditional expectation, which is computed with respect to F0, but once you know the solution of the BSDE, you know the whole future evolution of your conditional expectation. Also, you know the hedging strategy. So, in general, as I said, in order to have a minimum of realism, we assume that we do not trade a single product between the bank and the counterparty, so we have V hat here as a simple portfolio of claims, which have, for the sake of simplicity, all the same maturity. Of course, in practice, this is not the case. So, I mentioned as a motivation for the introduction of valuation adjustment counterparty credit risk. So, the idea is that you have two agents, the bank and the counterparty, okay, and since they are entering this whole family of contingent claims, they exchange cash flows. Just think about a portfolio of interest rate swaps if you want, okay? Now, of course, before the financial crisis, no one could default, and then people started to realize, hey, this is not so realistic. So people started to think in terms of, first, they introduced the possibility that the counterparty might default, okay? And this gave rise to the so-called CVA, so let me write it here, which stands for credit value adjustment. But then around, I would say, 2012, 2013, people started to say, okay, but look, also the bank could default, and this gave rise to the debt value adjustment. Okay? So, and in order to take into account of this possibility, we introduce two different additive adjustments, okay? So in standard credit risk, you adjust the discount rate. In counterparty credit risk, you add and subtract things, okay? And these terms, CVA and DVA, are added and subtracted to the perfect risk-neutral price in order to compute the price that takes into account this friction, namely the possibility that both counterparties could default. In order to reduce the outstanding exposure, okay, people can exchange collateral, okay? So we all know what a margin call is from the way futures are traded. When you trade into a future, you exchange margins every day. Collateral means simply take any standard derivative and turn it into a forward. So you look at the mark-to-market of your portfolio V hat, okay, and then with your counterparty you start exchanging cash flows. Most of the time you just exchange cash as a way to guarantee you against the default of your counterparty. And of course the collateral reduces the exposure, but the collateral is computed again at the portfolio level, okay, because you typically have some netting effects between the different swaps. It could be that one swap has a positive mark-to-market from your perspective and another swap has a negative mark-to-market from your perspective. So when you compute... Sorry? Okay, sorry, as I announced that this was going to happen. So I was saying that when you... so of course when you compute the collateral, you compute the collateral on the whole set of transactions that are in force between the bank and the counterparty. So your valuation is no longer linear in terms of your trades. The valuation becomes highly non-linear because the valuation of a single product becomes a portfolio-wide problem. So in these two plots here that I have, you see the difference between one single path of the exposure, for example, of a portfolio, okay, and you see here the effect of exchanging collateral according to this rule that you have here below, okay. So essentially what you obtain is once you subtract the collateral, you reduce the amount of your exposure so that your overall risk is reduced. So, as I said, as soon as we started to include more and more frictions in the aftermath of the financial crisis, people started to introduce more and more valuation adjustments. So, you see in the literal tool this acronym here, xVA, where X is just a placeholder, and then you put C, D, F, whatever. Okay? So the list that you have in this slide here is non-exhaustive. I would like to stress this. So I already mentioned the credit value adjustment, okay? So this is the adjustment that you introduce to the price, to the risk-neutral price, in order to take into account the possibility of the default of your counterparty. Then you have the debt value adjustment for the default risk of the bank. And then, in order to account for multiple curve issues and different sources of funding, you introduce the so-called funding valuation adjustments. The interested reader can look up this paper here, which appeared on Siphon, where we have even more valuation adjustments. Okay? So the equations that I will be showing now for the valuation adjustments are based on the paper here below. So how does xVA looks like? Well, it's quite non-trivial to compute, because you see that the CVA is essentially a hybrid product which requires you to know the future evolution of your het V. Let me remind you that het V is the whole portfolio, okay? Small m going from 1 up to capital M of the singles, the MT, okay? And of course it is inside the positive and the negative part, so it is if you want an extremely high-dimensional basket product, okay? And remember that the different V hat could depend on different risk factors, because you could have some options on foreign exchange rates and some interest rate products, okay? Because between the bank and the counterparty, we could have a plethora of instruments written on different underlines, okay? So, in principle, this object we had here could depend on several risk factors, okay? Several short rate processes, several FX rates, several indices, etc. So you see that I need to compute the whole story of V hat, okay, between small t and capital T, and then, of course, I need to take the conditional expectation. So,
excuse me, what is lambda?
Lambda are the default intensity of the bank and the counterparty in a classical reduced form framework. Okay?
Thanks.
Yeah, you're welcome. So, of course, as I mentioned previously, I'm subtracting the collateral, which reduces the exposure. Okay? And, okay, these are the recovery rates of the counterparty and the bank. The key message here is that this conditional expectation here involves, in order to compute this conditional expectation here, you just don't need the value of the conditional expectation with respect to F0, just when you price something. You really need to be able to compute future scenarios of your portfolio, okay? And this is where BSDE can help us. Another thing that I want to mention before I move to the next slide is that the valuation adjustments have different structures. So look here, I'm writing xVA, okay, as minus CVA plus DVA plus FVA, okay? So the CVA depends on a set of linear BSDEs which are hidden inside here, okay? So once I solve the set of linear BSDEs, this is a conditional expectation that you can compute by means of a standard Monte Carlo estimator. Whereas if you look carefully at the FVA, you see that inside the positive and the negative part I have the xVA itself. So the FVA has a recursive structure. So the treatment of this valuation adjustment will be different with respect to the first two, okay? So there are several approaches in order to compute this V hat, okay? So, I don't have time in order to dig too much into the literature. What we do here is to use the Deep BSDE solver introduced by Ehan and Jentzen in 2017. Okay? So, what is the idea? So, as I mentioned previously, each European contingent claim solves a forward-backward stochastic differential equation. Okay? So the Deep BSDE solver is an algorithm which allows us to solve forward-backward stochastic differential equation of the following form. Okay, so you have a forward SDE of the usual form. Okay, so this will be the multidimensional SDE which describes the risk factors. Okay, and next to it you have the BSDE for the different European contingent claims, okay? So you will have the usual terminal condition, okay? This function here, which is called the driver, and Z is the control, or if you want in financial terms, your hedging strategy. So this is, of course, the forward-backward system in continuous time, okay? What we want to do with this solver proposed by Ehan and Jentzen. So you can think about this forward-backward system as the solution of this stochastic control problem that we discretize in time. Okay? So you want to minimize the squared distance, the expected squared distance between the terminal payoff and the terminal value of your BSDE. Okay? But now look subject to discretized dynamics. So we work in discrete time now. We perform an Euler discretization of the forward-backward system. Okay. So here you have the standard Euler scheme for X. And here I am applying a forward discretization of the backward SDE. Okay. And you see that the variable over which we perform the optimization now are the initial value of the BSDE, y, and we parameterize Z, the family of controls, by means of several neural networks, one neural network for each point in time, and each of these neural networks depends on a set of parameters, weights and biases. Okay, so the minimization now runs over the initial value of the BSDE and over all the weights and biases of all the neural networks that parameterize your control. Okay, so this is the idea. So turn your forward-backward SDE into a stochastic control problem. So how does it work? So there are some error estimates which were introduced by Han and Long. Okay, so you can control this between the true BSDE and the BSDE parameterized by the neural networks by means of this expected value here. Okay? And this expression in the end depends on the expression power of the neural network, and in practice it depends also on the optimizer that you are employing. So how does our algorithm for the computation of xVA look like? So the first thing that we need to do is we need to generate the scenarios of V hat. Okay, so I need to generate the scenarios of the clean value of my portfolio. Okay, so the idea is as a starting point, I want to run the Deep BSDE solver in order to solve the linear BSDEs which are satisfied by the family of European contingent claims. This gives me the hedging strategy of each European contingent claim, which is now of course parameterized by the neural networks. Okay, and what we do is we save the optimizer, so that we will be able at a later point in time to perform a simulation. We will simulate trajectories of our BSDE as if it was just a standard process that you simulate in the context of the Monte Carlo simulation. Okay, so we first run the algorithm on each BSDE and we store the optimizer. Okay, and what we have here is just a discretized version of this system. So once we have the simulation of our BSDE parameterized in terms of neural network, we can compute directly CVA and DVA, and this is the topic of algorithm 2. Okay, so for the non-recursive evaluation adjustments, which have this simple form here, you see they merely depend on the hat, on the mark-to-market of the portfolio. Okay, so these are simple conditional expectations, so what we can propose is just a standard Monte Carlo estimator. Okay, so this is algorithm 2, which is enough for the non-recursive evaluation adjustments such as CVA and DVA. So let me provide some examples for this methodology. Easy motivating example. I simply work with a one-dimensional Black-Scholes model. Okay, I am not advocating the use of this algorithm for a one-dimensional problem, but you can see this one-dimensional problem as a proof of concept of the algorithm. Okay, the true power of such algorithms will be in the multidimensional setting, of course. So I have a portfolio with a single contingent claim, so V hat is just this guy here. Okay, and CVA and DVA essentially depend on this discounted expected positive exposure and discounted expected negative exposure. Okay, and for simple European claims with Black-Scholes dynamics, these conditional expectations here can be computed exactly. So I have an exact benchmark against which I can compare the solution provided by the Deep BSDE solver. Okay, so let's say that you want to compute the exposure of a very simple forward. Okay, a simple forward. So look, this is the payoff here. Okay, so the payoff, the terminal condition of the BSDE is simply the terminal value of the asset minus the initial value of the asset. This is the payoff of a standard forward. Okay, so what you see here in the right panel, okay, is a comparison of what we obtained from the solver, okay, against what you obtained from the closed form solution, okay, and we achieve a very good fit, okay. What you have instead on the left-hand side is the simulation of the BSDE, okay. So the initial value 0, which is close to 0 here, because because the forward is assumed to be fair in this case, is the initial value of your contract, okay. What we have here are future trajectories of the contingent claim. It means that we are repricing, recomputing the price a lot of times, but this is easy because once you store the weights and biases of the neural network, it's a piece of cake to simulate these trajectories, okay. So we also have a slightly more interesting example, okay. So now I'm pricing a call option on an asset, okay. So practitioners from the xVA area know that the exposure profile of this contract is merely a straight line, okay. And you see again that I have a very good agreement between the expected positive exposure provided by the solver and the one provided by the closed form formula, which is essentially given by the Black-Scholes formula. And these again are paths of the option price, not paths of the underlying. Let me stress this again. These are paths of the option price. Okay. Okay. So, and for these experiments, we use very thin neural network architecture. In the end, we are in the one-dimensional setting. We just have 2 layers and a relatively small number of nodes. Okay. So a slightly more interesting example is when I consider now 100 underlines, okay, so D is 100 now, okay, so I want to compute my credit exposure on a basket call option with 100 underlines, okay. So this is something which is highly non-trivial if you use the standard numerical techniques, and this is where machine learning really helps us, okay? Because here we can really face the curse of dimensionality. So if you start considering the credit exposure of this product using standard algorithms such as PDs, etc., you will have a hard time, okay? But with our solver, we can simulate relatively easily whole paths of a contingent claim with which depends on 100 underlines, okay. So these are again paths of the contingent claim, okay. And again we still retain a good level of precision, okay, in spite of the high dimension of this example, okay. So far so good. I can compute CVA and DVA with a single application of the deep solver, okay? So now I want to go back to the shape of the valuation adjustments and recall you that in the funding valuation adjustment, this is the funding value adjustment, okay? We see that inside the formula for the funding value adjustments, I have xVA. So I have a recursive structure of the pricing equation, okay? So this will require a different treatment. So it means that here valuation is really non-linear. So now the BSDE that I need to consider is really a non-linear BSDE, okay? So, by using the approach that we present in this paper with Francesca Beggini and Immacolata Oliva, we can write down the dynamics of the xVA. It is given by a BSDE with 0 terminal condition and this driver here. So the first term here relates to the CVA, the second term here relates to the DVA, and the term in the last line refers to the FBA. So each, by looking at the driver of this BSDE, you can recognize the presence of each of these valuation adjustments. Okay? So, and look here, of course, Z now will be the hedging strategy for the valuation adjustments, not for the contingent claims. And this is something which is not so standard for counterparty credit risk. Okay, so most counterparty credit risk approaches just compute the valuation adjustments at time 0. Okay, hedging of the xVAs is a much more difficult thing to do. Okay, but we can do it with our BSDE and deep learning approach. So the idea now is I want to tackle this non-linearity effect, this recursive structure. How shall we do this? We can do this by means of a nested application of the Deep BSDE solver. So the idea is, first, you apply the Deep BSDE solver in order to estimate the future evolution of the hat, okay, the mark-to-market of your derivative portfolio, and you store the solution. After that, you start running the Deep BSDE solver once again, but this time we want to approximate this BSDE here, okay? So remember that inside the driver of this BSDE, I have the hat, okay? So when I am trying to solve the second BSDE, okay, I will need to recall the simulated BSDE that I obtained from the first solver. Okay, so this is why I say that we have a nested application of the BSDE solver, because I have the hat here inside. Okay, so the idea is, of course, you apply algorithm 1, which gives you the V-hats, the mark-to-market of the portfolio, and then you apply again the solver. Okay, so within the stochastic gradient descent loop, okay, I will be recalling every time the BSDE of the clean value. And this here, what you see here is just a discretized version of this BSDE here, okay, where now I am parametrizing again the controls by means of a second family of backward stochastic, a second family of artificial neural networks. Okay, great. So we were able to obtain some a posteriori error bounds for this algorithm 3. Okay, essentially we have been adapting by means of an adaptation of the ideas of Han and Long. We were able to compute this a posteriori error bound. Here you can find the details in the paper. Okay, so you see that I am controlling the distance between the true xVA and the xVA obtained by the discretized and approximated BSDE. By means, you see that I have here the distance between the true mark-to-market and the approximated mark-to-market, and then this final term here, which depends on xVA tilde capital T. And there is no other term here because the terminal condition of the exact BSDE is 0. Okay, so you have a terminal condition which is 0, so this is why you have this appearance here of the final term. Okay, so let me try to provide evidence for the application of this solver for nested evaluation adjustments. Okay, we compute the FBA, so I assume that there is no default risk, or there is only funding risk. Okay, it's only illiquidity if you want. So I want to compute now the funding valuation adjustments, okay? And for the easy example that we were able to obtain here, we were able to obtain a closed form solution for the conditional expectation, and with our Deep BSDE solver, we were able to approximate it with a very good level of precision. Okay, so there are also several interesting things that we did in this first part, such as we were able also to look at the hedging strategy, but I don't have time to do that because I would like to move to the second part now. But essentially, these are the conclusions for the first part. So by approximating the BSDEs via deep learning, okay, we can set up a whole portfolio-wide risk management framework. Okay, So we are able to perform pathwise simulation of the collateral. I will not discuss this in detail, but anyway, our approach is flexible enough in order to account realistic collateral specifications. We are able to talk about xVA hedging, which is slightly difficult to do in practice. And we are also able to tackle the recursive structure of some valuation adjustments. Okay. So for those who are interested, there is a preprint on the archive, and if you go on my GitHub page, you can also download the Python library and play around with the solver. Okay. So this is it for part 1. So, and what is the first limitation that you might observe in part 1? So the driver is only a diffusion. We only have Brownian motion in the first part. Okay. So to us, it looked quite natural to complicate things a bit, if you want, and then ask ourselves, okay, how would the Deep BSDE solver look like if we wanted to solve BSDE with jumps? Okay. So in this second part, I will be leaving the motivation provided by counterparty credit risk, and I will do a step back to a more general setting, okay? The general setting of a forward-backward stochastic differential equation in the presence of jumps, okay? So, if you want, the setting is the same as before. So, this is the canonical process that we were considering also in the first part of the talk. So, what we want to introduce now is, of course, the presence of jumps, okay? So, with respect to the previous one, we introduce a compensated Poisson random measure, okay, and we introduce standard assumptions on the coefficients of our forward dynamics, which ensure the existence and uniqueness of strong solutions. So, associated to this forward SDE, we have a backward SDE again, okay. So F is still the driver, okay, which depends on time. It depends on the forward process X. X is the forward process. It depends on itself. It depends on the control on the Brownian part. And then, okay, here if you want, you could write a general U, but in the application, what you most of the time use, you have a dependence with respect to the integral of this further control process U, and nu here is the Levy measure, okay? Is the Levy measure of associated to your Poisson random measure, okay? So by introducing jumps now, we don't only have Z as a control, we also have this U here, okay? So far so good. Of course, we introduce a standard assumption ensuring existence and uniqueness of our BSDEs. Okay, we have some Lipschitz linear growth on etc. So, now it is time to ask ourselves, okay, what is at the heart of the solver? So, at the heart of the solver is the famous link between partial integral differential equations, okay, of this form, and backward stochastic differential equation, okay? So, we have, in general, our solver will be treating a partial integral differential equation of this form. So, in the diffusive case, you have this term here, okay? What you introduce when you have jumps is this second term here. This is why we call this equation a partial integral differential equation, okay? So this is the standard when you look at Levy processes, for example, okay? So essentially, a BSDE solver is a machinery which allows us to solve PDEs of this form in very high dimension, okay? I did not mention PDE in the first part, but from the Feynman-Katz theorem, this is what it is about, okay? From the Feynman-Katz theorem, we have a strong relationship between forward-backward stochastic differential equations of the form that I just gave you and this sort of partial integral differential equation. And in particular, we know that the BSDE, okay, is associated to the function u which satisfies the PID. Okay, so if you want, the BSDE is the time evolution of the function u that satisfies the PID. Z, okay, is associated to the first derivative of u with respect to the space dimension times sigma, which is the diffusion coefficient in your forward dynamics. And then u involve, which is the control that we place in the jump component, simply involves the difference between the function u after a jump minus the function u just before the jump. Okay? So, of course, if you are familiar with the standard setting without jumps, ux here is your usual delta hedging strategy. Okay? So, also in the first part, we were looking at the system of forward-backward stochastic differential equation from the point of view of stochastic control. This does not change in the second part, because you see that the functional that I want to minimize is still the same, okay? It's still the same as before. I still look at the difference between the terminal payoff and what is produced by the BSDE, okay? Over the initial condition of the BSDE, over the control for the Brownian part, and over the control for the jump part. So we want to minimize this squared distance here, subject to the dynamics of the forward-backward system. Okay? So, the idea is we want to extend the logic of the deep solver of Hehan and Jentzen, which is exactly like in the previous part of the talk, the following. So you start from the forward-backward SDE, you discretize it with a standard Euler-Maruyama discretization. Okay, so this is standard Euler-Maruyama. And then you say, okay, for each time step, my control now is an artificial neural network, a feed-forward neural network. Okay, so now your minimization runs again over the initial condition of the BSDE and the parameters of the neural network. Okay. So how does the picture change when we introduce jumps? So as a starting point, let me assume that the Levy measure integrates the whole of RD. So I'm talking about compound Poisson processes. Okay, I'm talking about jump processes with finite variation and finite activity. Okay. So this means that when I discretize the forward component, okay, I can easily write something of this form, and I can split the stochastic integral with respect to the compensated Poisson random measure in the following way. So these are the jumps, okay, so the first term here is the jumps that occur between Tn and Tn plus 1 in my Euler discretization. And this here is the compensator of the jumps. And I can split it because I am in the finite activity and the finite variation situation. Okay? So how does now the BSDE look like? So what we do is first the following. So I discretize again my BSDE. Okay, look, so this is again an Euler scheme. Okay? And then I substitute the shape of Z and of U, which is coming from the Feynman-Catch theorem. Compare what I just highlighted in yellow, okay, with the Feynman-Catch theorem, you see? Okay, so I plug already a certain shape for Z and U, which will help me somehow, okay, which will help me give a bit of structure on my discretization schema. And you see that now, okay, in the stochastic integral part of the BSDE, I have this term here. Okay, let me use a different color. I have this term here. So you see U after the jumps minus U before the jumps. This is coming again from Feynman-Catch. You see U after the jumps minus U before the jump. Okay. And of course, now here, you see, this is the compensator of the jumps of the BSDE, okay? So the last term is the compensator of the jumps of the BSDE, which of course involve the difference of u before and after the jump. And notice that this is an integral in Rd, where d could be very high, okay? So now I am in front of a bottleneck from the numerical point of view, okay? Because if the dimension d is very high, then I have what? A very high dimensional integral, and okay, if you are in dimension 1, you can use the standard quadrature formulas, but if the dimension is very high, there is no hope that you can do it, okay? So, how can we tackle this situation, okay? So, what we propose is to introduce two families of artificial neural network, okay? So, the first family of neural network, okay, will parameterize directly the function u. The function u, let me remind you, appears here, okay, here, and is also the integrand here, okay? So, with the first neural network, I just parameterize u, which is the solution of the PID. But the trick that we propose now is the following. I don't want to perform this very high dimensional integral in dimension 100. No way I want to do it. Okay? So what I want to do is to introduce a second family of neural networks, and this second family of neural networks will directly approximate the whole integral. Okay? So I want to avoid this very high integration problem. Okay? So in a certain sense, I need to teach the second family of neural network how to correctly compensate the jumps of the BSDE. So this is the tricky part of the algorithm. Okay? So you see, once you start doing things like this, you see that now the discretized BSDE in terms of the neural networks looks like this. So you have the BSDEs here and here, and notice that here I am computing the gradient of the neural network because I have the first derivative of u there, but this is easy because with TensorFlow you can compute you can use automatic differentiation, so that's not a problem. And you see that here I have the second family of neural network that parameterizes all the compensator of my jumps. Okay? In order to avoid the big numerical integral. So how do I estimate the optimal parameters now of the second family of neural networks? This is the big issue, okay? So the issue is, well, if you think closely, you just have to remember that the stochastic integral with respect to a compound Poisson measure is a martingale, okay? So each of these guys here, the expectation of each of these guys here should be 0, okay? So now, recalling what a conditional expectation is in terms of minimization of distance in L2, what we propose is to introduce a second penalty term inside the minimization, okay? This second minimization, this second penalty here will essentially force the compensator to be such that the compensated discretized integral is approximately a martingale. Okay? So once you do this adjustment, the loss function of the algorithm now is the previous loss of the algorithm plus this second term here. You see the summation here is running over time. So now m now is running over different points in time here, okay? So for each point in time, I have a different neural network for the jump compensator, and at each point in time, I want to force the compensator to compensate in the right way the jumps, okay? So, and then you simply run your stochastic gradient descent so you can recycle the machinery of the solver, okay? And this works quite well, okay? I have some example in the last final minutes, okay? So the first thing that we do is I compute things with a totally trivial BSDE. Okay, I just test the martingale property of the asset if you want. Okay. So so I have a totally trivial BSDE of this form. Okay, which is associated to this conditional expectation, which is just testing the martingale property of the asset. So, is the Deep BSDE solver able to obtain a BSDE that reflects the martingale property of the asset? Answer, yes. Okay, so the red line is 1, okay, our test value, because I just put the initial value of the asset at 1, and I'm able to obtain from the solver, again, the martingale property of the asset. So if you want, this is a first sanity check of our algorithm. The second is, okay, a European collapsion on a Merton jump diffusion model. And again, this works nicely. Okay. So Merton jump diffusion, finite activity case. Okay. And then the big high-dimensional example, again, the collapsion with 100 underlines. So I take 100 Merton jump diffusions and I compute again the price of a basket option. And again, I have good results. I can approximate quite well the price. We have encouraging results, even though the computational time, of course, increases because now we are in a very high-dimensional setting. And finally, okay, what about the infinite activity case? Okay, so the solver so far handles only the finite activity case, I told you. Well, in case we have the infinite activity case, our idea is to use standard simulation schemes for Levy processes. Okay, if you just look at the book by Konstantakov and you want to simulate the CG&Y process, one of the classical way to do it is, okay, you fix a threshold epsilon for the jumps, okay, and then you say, okay, anything that has a jump size larger than epsilon is a jump of a compound Poisson process. Anything which has jump sizes smaller than epsilon can be approximated by a Brownian motion. Okay, so the idea is I substitute the true forward SDE with an approximated jump diffusion. Okay, and then I can use again the solver. So I see that time is running faster. I don't have the time to expose the technicalities here. I just directly jump to the example. Okay. So let's say you have a CG&Y, okay? You can write the CG&Y as the difference of two subordinators, okay? Then you approximate each subordinators by means of a jump diffusion. You combine the two approximating subordinators, okay? And you obtain an approximated Levy process of this form here, okay? So, and what we did here is a sanity check. Since for the CG&Y we know the characteristic function, we can invert the characteristic function using the fast Fourier transform, and you get a numerical density. This is the blue line. And then, okay, we simulate Monte Carlo paths of our jump diffusions. We plot the histogram, and these are the orange bars. Okay, so the histogram for Monte Carlo is very close to the FFT-based density. So, okay, at least this is the first sanity check. And then, once I have this jump diffusion approximation, I can try to approximate an option price on a CG&Y process. And again, we get encouraging results. And the red line was computed with the true CG&Y process using the inversion of the fast Fourier transform. Okay? So, in this way, we are able to tackle also the infinite activity case. So, what we did in part 2 essentially was generalizing the algorithm of Hahn and Jentzen to the case where we have jumps of finite but also of infinite activity. We have a preprint on which we are working. We are finalizing the details. We should post it on the archive in the next couple of weeks, hopefully.